Hello, my name is Kelsey Barber, and I'm going to be talking about the thermodynamics of Hadley cells. Before I go into what Hadley cells are, I want to talk about reasons why they're important. And to do that, I want to look at the distribution of climate zones on the Earth. So what I have boxed here, there are two red boxes showing regions where there are large amounts of deserts. So the two regions are about equidistant from the equator. In the northern section, one of the largest deserts in the world, the Sahara, is included within this box. And in the southern section, Australia, the desert in Australia, is included in this box. So basically, just within these two regions, there are large deserts, there are a lot of deserts. Then looking at the equator, around the equator, there is a high distribution of tropical forests, rainforests, and that indicates that at the equator there is high levels of precipitation. So I think looking at these two distributions, the question that follows is what is causing this distribution of climate zones and these distributions of precipitation? So the main reason for that is circulation within the atmosphere. So within the atmosphere, there are three main cells of circulation, and those are the Hadley cell, the Ferrel cell, and the polar cell. And in this presentation, I'm going to be focusing on the Hadley cell, which is the circulation cell that's located on either side of the equator. So the way that Hadley cells work, basically heat comes in at the equator, and at that point in the equator, the air in that region is heated up. There's a lot of evaporation happening, so water vapor is out of the air. And as that air heats up, it rises. So as it rises, it pushes the air on top of it to either side of it. And as that air is pushed along at high altitudes, it cools down. And when the air cools down, the water vapor within the air condensates, forming clouds and eventually forming precipitation, which causes the regions of rainforest along the equator. So as that air cools and is pushed along at high altitude, eventually it will cool to the point where it can sink. So as it sinks, it pushes the air underneath it out to the sides, causing a divergence zone. And that air in that divergence zone is very dry. There's no more water vapor left in it. And so that is labeled by the dry region shown in this image. And at those dry regions, that's where we see the strips of desert within the earth. So once the air sinks and reaches the surface of the earth, it is either pushed towards the pole or towards the equator. The air that is pushed towards the equator just repeats the same process within the Hadley cell. And kind of the context that I want to talk about the thermodynamic properties of Hadley cells through is looking at how they have changed with climate change over the past 32 years, and a trend that we've seen in the distribution of deserts within the Earth is that deserts are migrating poleward, which shows that Hadley cells are migrating poleward, and basically areas of desert are extending. So the paper that I read to understand how climate change is impacting Hadley cells is called The Contributions of the Hadley and Ferrel Circulations to the Energies of the Atmosphere over the Past 32 Years. And it was written by Wang and McElroy. And most of the diagrams throughout this presentation came from that paper. So the first thermodynamic diagram that I'm going to be addressing today is this pressure versus volume diagram. The x-axis in this diagram is specific volume, so that is volume divided by mass, and the y-axis is pressure. And an important thing to note looking at this diagram is that the upward motion, so the air moving upward, is shown in a blue line here, and the specific volume for upward motion is always greater than the specific volume for downward motion, which is shown by the red line. So using this pressure versus volume data, we can eventually calculate work using this equation. So work is equal to the closed loop integral of pressure multiplied by change in specific volume. And again, specific volume is volume divided by mass. So looking at this diagram, this is the change in specific volume on the x-axis versus pressure on the y-axis. The area under that curve is equal to work. So basically, the work in this system is 1.9 kilojoules, and that is work that the air parcel is doing on the system. Looking at entropy within the system, entropy is equal to C sub P multiplied by the natural log of theta. So in this case, C sub P is the specific heat of dry air with pressure held constant, and theta is the potential temperature, which is the temperature that the parcel of dry air would have if it were brought from its initial state to standard pressure adiabatically. Looking at the second law of thermodynamics, it states that the change in net heat within the system is equal to temperature multiplied by the change in entropy. And in this case, I want to say that the change in heat within the system, it is a change in heat both coming into the system, so the solar energy that's coming into the system, as well as the release of latent heat. So basically, as water vapor, it basically stores heat. So as water vapor condenses, it releases latent heat. Both the release of latent heat and heat from sources are taken into account when looking at the change in net heat within the system. So looking at the change in heat within the system, this is a graph showing entropy on the x-axis and temperature on the y-axis. The small difference between the blue line and red line would show upward motion and downward motion indicate a small thermodynamic efficiency. So efficiency is basically calculated by looking at absorbed heat divided by the absorbed heat with net positive heating. And the thermodynamic efficiency within this system is 4.3%. So a very small amount of the heat that is going into the system is actually converted to mechanical work. Looking at the power of Hadley cells, one way to visualize the calculation of power within Hadley cells is looking at two concentric loops, like are shown here. And basically mass is moving between those two loops within the system. So M is equal to the mass in between the two loops. T is equal to the time that it takes to travel between the two loops. And F is equal to the mass flux between the loops. Now, looking at a calculation of work for this system traveling through one loop in the system, work is equal to the mass multiplied by the closed loop integral for pressure multiplied by the change in specific volume. And we can rewrite T to be equal to mass divided by the flux of the system. So that is the change of mass over time. Then substituting this new equation for work into the power formula and the equation for time into the power formula, power is equal to flux multiplied by the closed path integral for pressure multiplied by change in volume. And this is a graph showing the change in power of the Hadley cell over the past 32 years. So observations of power of Hadley cells were taken monthly as well as yearly. And then a linear line was fit to this data. So looking at this data, obviously it's like very messy. And so the linear fit had a fairly high R-squared value of around 0.3. So take that into account looking at the conclusions of this. But the linear fit has a slope of 0.5 terawatts per year. So based on this data, there is a general trend of increasing power of the Hadley cells over time and with climate change. So talking about the thermodynamic characteristics of Hadley cells that was covered in this presentation, Hadley cells function basically like heat engines. Work is done by an air parcel on the system, and it's a fairly inefficient system, and generally power has increased over the last 32 years. So connecting those thermodynamic properties to climate change and back to Hadley cells, basically what we know so far just by looking at distributions of desert and desertification of the earth, Hadley cells seem to be moving poleward and deserts are extending poleward. So another way that we can learn about how Hadley cells are changing with climate change beyond just looking at like geography is understanding the thermodynamic properties of Hadley cells and how those are changing with changes in our atmospheric temperature. These are the sources from this presentation. And I'll now open up the floor to any questions. Thank you for listening to my presentation.